Welcome to this Maths Online CPD course delivered by Charlie and Alison from Enrich on teaching probability using some Enrich tasks. I'm delighted that you can all join us this afternoon on what is a very bright and sunny day here in South London, and I hope it is also nice weather where you are today. Just got a couple of things to tell you about before I hand over to Alison and Charlie. So I'll just move the screen on. Just a few logistics. If you aren't speaking, please do mute, as this does help us avoid any background noise. Do use a chat box for questions, comments, and resources. I know Charlie and Alison will be posing a few brain teasers in there for you to type in. Do look out for our post-course email, which will share the resources from today's course and the video of the session, which we will process afterwards. And then at the end, a short survey will load at the end of the course in your browser. Do please take the time to fill that in. All the feedback that we receive, we do read and act on to improve further courses. And of course, further courses and information about the PTI can be found on our website, which is on the screen now. So I'll just move on to talk about the aims of the day, which are to reflect on how to teach maths in an engaging, connected, and enriching way, and how tasks from the Enrich secondary curriculum and mapping document can be used to develop students' reasoning and problem-solving skills, whilst offering opportunities to build fluency through purposeful practice. Excellent. Well, without any further ado, I will hand over to Alison, I think, who's going to start things off with Charlie. So, Alison.
Thank you very much, Patrick, for that introduction. Yes, hello, everybody. Wonderful to be here this afternoon. What Charlie and I are going to do over the next hour and a half or so is take you through some of our favourite probability problems from the Enrich website. Hopefully give you a chance to have a go at them as well, and get you thinking about how they might be used in the classroom, but to tell you some of the key messages that we think are behind them in the classroom. So we're hoping that some of you will have had a chance to look at our first problem that we're going to share. So it's called In the Bag, and I'm just going to share my screen with you all. So hopefully you can now see the interactivity from In the Bag. I'm going to put the link in the chat as well, so if you want to have a play with it on your own devices in another window, that it's there for you, or there for you to have a look at afterwards. But Charlie, shall we have a go at actually playing this to see what would happen if we were students? Does that sound like a nice way to start, do you think? Okay, so do you want to explain how the interactivity works, or do you want me to?
I'll start, and then you can put me right if I've so we start with a score of 500. We know that the bag contains 10 marbles, and there may be some red, some blue, some yellow, and some green, but they're not necessarily all there, are there? There might just be 3 of the 4 colours, or 2, or even just 1 of the 4 colours. Indeed. Okay. And what we're imagining is putting our hand in the bag, taking a marble out, making a record of the colour, and then putting it in the bag, mixing them up, taking another one out, making a note of the colour, doing this 10 times, and the computer will tell us what the result is of pulling a marble out 10 times. Okay, so shall we show what that bit looks like then? Okay. So if I click perform 10 random viewings, you can see ball comes out and then goes back into the bag each time. So we're talking about situation where there is replacement, but I've done 10 trials, and in those 10 trials a red marble came out 6 times, a blue one came out once, a yellow one came out once, and a green one came out twice. So we know there is at least one of each. Yeah. It's likely that there are more reds than anything else, but it's not completely clear. I mean, we might have been lucky and got exactly 6, which matches how many there are. So we might want to do that again and just see how that compares. So right now we've got 60%, 10%, 10%, 20%. So let's try and keep that in our head. Do you want to do another 10 viewings?
So this time it doesn't show you each one going out. It just shows you the result of the 10 dropping down onto the thing, because once you've seen the animation, we kind of know what's happening here. And if we want to do lots of viewings, we don't want to have to wait for it to animate every time. So what happened on that second one then?
Well, we must have got many more yellows and greens.
And not as many reds that
not
time.
Not as many reds. So on average, there's still more reds, but it looks like the first time was an unusual number of reds. So I don't feel confident to be able to guess what's in the bag right now.
Okay.
Perhaps a third go would be good.
There we are.
Wow, there are now more greens than reds. That's unexpected after the first one. Now, what's happening on the right-hand side is that our score is going down by 10 each time. So
yes, it sort of costs 10 points to have another viewing, doesn't it?
It does. And then when we decide we're in a reasonably confident, well, we may want to take a risk, a chance, and stop using up points. There is, we can score, I think it's 150 points if we guess exactly right what's in the bag, and something like 100 points if we get 9 out of 10 right.
Yeah, and if you get 8 out of 10 right, I think it's a 0 score, but if you get fewer than 8, it's like a negative score and you lose points.
Yes.
So there is a penalty to trying to be too risky.
Yes. Okay.
Well, let's give everybody a chance just to quickly jot down. I'm assuming everyone's got a piece of paper handy, and just jot down what you think you would guess for this. If anyone wants to put in the chat what their guess would be, and then why don't we play a game, Charlie? Why don't we make it so that you tell us what your guess would be, and let you have, what do you think, maybe 3 rounds worth of goes and set me a score to beat?
Okay.
So we'll just see if anyone wants to pop into chat what their guess would be for the distribution of the beads, the marbles in this one. But have you got something in mind that you're ready to guess?
Me?
Yeah.
Is this going to be the first round of my game?
Well, that might not be very fair, because I didn't tell you that it was going to be. Do you want it to be, or would you rather start from scratch?
You're going to be a risk taker. Or
I'm going to be a risk taker, definitely.
Oh, okay.
My strategy is going to be high risk, high reward.
Okay, well, no one's had a go at the chat here, so I'd like to have another round then before making up my mind.
Okay, so you want to guess again?
Yes,
View again.
Yes.
Okay, there we are. So altogether, you've got just under 30% red and green, just over 30% by the look of it yellow, and then about 15%.
I really want to have a chance of getting all 150 points, so I'm going to have another 10 random viewings, please.
Okay. Did that help?
Okay, I'm going to go for 2, 2, 3, 3, please.
So 2 reds, 2 blues, 3 yellows, and 3 greens. Okay, let's see how you did. 2 blues, 2 reds, 3 yellows, and 3 greens. So you got full marks, 150 points.
I decided that first go, when we got all those reds, was really not representative.
Something was fishy.
Okay, good. Okay.
Okay.
So I'm doing 3 rounds, am I?
Yeah.
Alison?
So next round 2. So I assume you want to have a look what's in the bag.
Come on then. So I'll have, do that at least 3 times.
Okay, so that was once, that's twice, that's 3 times. Notice there that we didn't have any yellows at all until the 3rd time.
Wow.
So that's quite interesting.
Okay, I'll do one more go, please.
Okay.
Okay, one more go. Patrick has guessed. Patrick, you need to have them adding up to 10, please. So you need to choose one more.
Okay.
Yes, I was going to say 3313, Patrick, but the Reds.
The Reds have pulled away a little bit.
Yeah, so either blue or green may not be 3. I'm going to do one more viewing, please.
You're burning through all of those extra points you earned.
I know. Okay, so I'm going to go for 3312, please.
3-3.
Oh no, I've got that wrong. 4312.
4312. Okay. So the nice thing about this is, as well as learning probability, we can also do numbers that add up to 10. Okay, I'm going to start your next round for you, Charlie, and do your first viewing. There we are.
So did I get 100 points there?
You did, yes, 9 out of 10. So no blues this time on the first viewing.
Keep going. So I started with a score of 500. I've got 620 after 2 rounds. Okay, keep going.
That's 3 guesses now. Sorry, 3 viewings now.
Okay, one more, please. Okay, I'm going to go for 3124, please.
3, 1, 2, 4. And notice that until I've got 10 marbles in there, it won't let me submit the guess. So if you can't add up to 10, it's fine. Let's have a look how you did. 9 out of 10 again, so another 100 points. So after 3 rounds, Charlie, your score is 700. Right, what I'm going to do then is I'm going to play 3 quick rounds with my super high risk strategy, which is just going to be whatever the distribution is after the first viewing. I'm going to guess that it's going to be that, and we'll see what happens. So let's reset.
I wonder whether our participants think that this, whether your strategy's got any chance. Would people like to write in the chat? Do they think Alison will score more than 700 points, or will I be the winner after 3 rounds? I'm curious to know what people think.
Well, I won't press the guess button just yet then. So my strategy is literally to watch once what happens and then assume that the 10 marbles I've seen are the 10 marbles that you...
So to win, I think you're going to have to get 3 9 out of 10s.
Okay.
Because that'll give you 300 points, but you're going to lose 30 points. So you'd win. So actually, you could even do 2 viewings if you wanted to and still beat me. Actually, you could do 3 viewings, and as long as you got 100 each time, you'd beat me. You'd get 710.
So Andrew thinks I'm going to lose. So let's see how I get on with round 1. So guess.
Oh, wow.
Okay. So I got all correct 150 points. I'm going to try the next round. Okay, so this time I've got 2 reds, 1, 2, 3, 4, 5 yellows, 1, 2, 3 greens, and no blues. So let's see what happens. Oh no, there's a blue there. Oh, so I got no points that time because I only got 8 out of 10 right. So, but it's okay. I've still got one more round to catch you up.
I think I had about 630 after 2 rounds.
Yeah, I think you're right. Okay, so this time 3 reds, 5 yellows and 2 greens. I'm crossing all of my fingers and my toes. Oh, there's a blue in there. I definitely haven't got maximum points then. I got 9 out of 10. Oh, so
no.
because of that super lucky start that I had in 3 rounds, I won. But when we were talking about this the other day, when we were planning it, we said that we'd probably play 5 rounds, and we changed to 3 because it does take quite a long time. And I think the more rounds we did, the more likely it is that my high risk strategy would not have paid off. But we wanted to share this because
Why do you think this, Alison?
Why do I think this? Because in so many of your goes, Charlie, there would be one where you didn't see a colour at all in the first drawing, but then it appeared in the second or the third drawing. So this idea that because I've seen 10 marbles, I will have seen every one time. This feels like the sort of misconception that kids often end up with about the link between experimental and theoretical probability. And the theoretical probability to model what's going on here is actually really quite complicated, because you've got 4 colours, you've got the combinations that can add up to 10, and then you're effectively doing a tree diagram with 10 layers and working out the probabilities, and then you're seeing the probabilities and then trying to backtrack that to what it would be. So I don't think I would necessarily use this as an activity for modeling the connection between theoretical and experimental probability, but I would use it to get students thinking about what they know from the results of an experiment and where they need to be cautious about what an experiment is telling them. And I think this is going to link in with some of the things we're going to talk about later with regards to, once something has happened, then the probability of that thing happening is 1 because it's in the past, it's happened. But that doesn't tell you anything about predicting the future, because unlikely stuff does happen sometimes. And you can't tell by looking at the results of the experiment whether it was an unlikely thing or not. And we've got some other really good examples of that to discuss as well.
But it also highlights the value of doing more and more rounds. And the more rounds I did, the more confident I became that I was on the right track. And I don't think I ever got an 8. I always got either 9 or 10. You got an 8, and you're more likely.
Suspect I would have got less than 8 if we'd played on. I suspect I would have completely bombed out at some point.
Yes.
Because my strategy was not a good one.
Well, but I can imagine students, I could imagine doing this with students and saying, try to test out a strategy and then compare it, just like you and I did. And maybe I would have my strategy, which is I will always have 3 lots of 10 random viewings and then make up my mind after that. And others might want to play safer in the hope that they'll get 150 points more often than me.
Yeah, and you've also got that we can start to discuss strategic thinking, which is important in lots of areas of maths, because the fact that it's a game and it's got this scoring element to it, you might want to change your strategy depending on what your score is. So when you said to me, oh, you're on 620 now, that's what I was on after 2 rounds. I could have then changed my strategy to try and beat you because I knew what my score was after 2 rounds. On the other hand, Andrew's just popped in the chat there that trying my strategy, he got 320 points after 3 rounds. So that's more what I would have expected to happen with this high risk strategy. The other thing that it brings up that is important when thinking about probability is the subtlety between something that only happens once and something that happens lots of times. Because if we are only playing 1 or 2 rounds, my high risk strategy I got lucky on the first go, and it wasn't a fix, Patrick. I didn't write this particular interactive, and I don't have the back end stuff set up to be able to fix it. But I got lucky, and that will sometimes happen, but you can't rely on getting lucky if you do something lots and lots of times. So when we pose questions in the classroom about, playing a game or any of those sorts of contexts, we need to make this distinction between a game that you're going to play once and a game that you're going to play many, many times. And I think it is important to talk about games in probability because, of course, the origins of probability theory were games of chance. The reason why mathematicians decided that they needed to formalize probability theory was so that they could win at gambling. And maybe we don't acknowledge that too much in the classroom, but we should at least give a small nod to it occasionally. Are you ready to talk me through the next problem, Charlie?
I am.
Okay, well, I'll get it up on my screen. Did you just
Shall we just show them the? Yes.
Okay.
So here we've got 3-numbered balls or marbles, and they're numbered 2, 3, 4, 5, 6. And again, we've got to imagine that they're in a bag, and we pull 2 of them out, and we add their scores. So here we're not replacing. It's different to what we just did. Here we're taking 2 out at the same time, 2 together, or one after the other, but we're not replacing the first one. We're adding their scores. And if the total is even, we win. If the total is odd, we lose. And there's interactivity accompanying it. Just to demonstrate how this works, let's just demonstrate the interactivity, and let's have the table rather than the graph, please. Okay, so let's just run it once, and they're shaken about, and 2 are selected, and unfortunately, the total is odd, so we've lost. And so on the table on the right, so far we've got a score of 0. Let's do another one, see whether we can be lucky this time. Yes. So our average is a half because we've won 1 out of 2 and we've lost 1 out of 2. Our score is 1. And I suppose the question that we have for you to start with is this going to be a fair game? If we played this a few more times, are our chances of winning equal to our chances of losing? So we want to give you a couple of minutes to think about this. And then in the chat, perhaps tell us whether you think it's a fair game or not. And perhaps if you can justify how you came to that conclusion, that would be really useful.
If anyone wants to put their microphone on at any point as well, you're very welcome to do so. We know that some people would rather share in the chat, but some people might find it easier just to speak to us. So we'll give everybody a couple of minutes of thinking time, and then we'll take some feedback.
I presume Patrick's happy with that. I mean, I know we're recording the session, but that shouldn't be a problem. Just to alert everybody that this is being recorded.
Yes, so if you do say something, then your voice will be recorded for posterity.
But we're quite a small group, so it would be quite nice to be able to talk to each other.
Right, so I'm going to have a go at this, Charlie. So I've got 2, 3, 4, 5, and 6. I'm just going to scribble away and decide whether I think it's a fair game or not. So Andrew's conjecture is that we're more likely to lose, so he doesn't think it's a fair game. So Patrick wrote down all the combinations and then worked out which ones were odd.
So presumably Patrick did something like 2 and 3, 2 and 4, 2 and 5, 2 and 6, 3 and 4, 3 and 5, 3 and 6, 4 and 5, 4 and 6, 5 and 6.
Okay. So then, having written them all down, then I can just go around and circle which ones are odd or which ones are even, and just count them up. So I'm going to count the even ones. So that's even, that's even, that's even, and that's even. So there are 4 out of 10 gives me an even, and 6 out of 10 gives me an odd.
So when you added 2 even numbers, it gave you an even total. And when you added 2 odd numbers, but if you had one of each, it gave you an odd total.
Okay, so I'm going to have a go at doing Andrew's method because he's described that in the chat now. So probability tree. So to start off with, there's a 3/5 chance of picking an odd and a 2/5 chance of picking an even. And then because we're doing probability without replacement.
Wait, I don't agree with this, Alison.
2, 4, 6. No, other way around. Yes, that's fine. I can get the eraser and rub it out. There we are. I just read what Andrew put. So 3/5 even and 2/5 odd. The nice thing is it doesn't matter. And then after I've taken an even, there's only 2/4 of them that are even and 2/4 of them are odd. And then if I've taken an odd, there's 3/4 and 1/4. I need to get my odds and evens consistent, don't I? So that's even and odd, even and odd. So even is now 3/4 and odd is 1/4. And then I can multiply, and now I can see where the 20ths come from, because quarters times fifths is giving me 20ths. And the ones that I'm interested in are either both even or both odd. So that's 6 20ths, and that is 2 20ths.
Yes.
So even is 8 20ths, and then that's 6 20ths and 6 20ths. So odd is 12 20ths. Yeah. Okay, so Laura, you did a sample space diagram, but you did it. I think I see what you mean. So I'm going to have a go at drawing Laura's method. So I can do a sample space diagram, and I can say that I've got 2, 3, 4, 5, and 6. 2, 3, 4, 5, and 6. And I know I can't pick the same one twice, so I'm going to have to get rid of this leading diagonal. And then I can work out which are odd and even. Now, the first time I ever did this problem, I worked out all the sums and then worked out which ones were odd and which ones were even. So I did 2 and 3 is 5, 2 and 4 is 6, and I wrote them all down in there. But I don't actually have to do that. I can just write down whether the answers are odd or even, because I don't need to know what the answers are, just whether they're odd or even. So 2 and 3 is odd, 2 and 4 is even, 2 and 5 is odd, 2 and 6 is even. And then 3 and 2 is odd, 3 and 4 is odd, 3 and 5 is even, 3 and 6 is odd. And I can carry on working out and filling in the sample space diagram. So Laura, what you did is very similar to what I've got written down here, except I only did the top half of my sample space diagram because I realized that the bottom half and the top half were going to be symmetric, so I cheated.
It's not cheating.
Okay, so I took a shortcut. Okay, so what's nice is that the different methods that have emerged from you all are quite similar to what we've seen when we've done this in workshops with students, isn't it, Charlie?
It is.
That depending on the age of the students and whether they've met tree diagrams before, I think mostly they tend to go for the listing all possibilities, and some will go for sample space, and then those who have seen tree diagrams and want to be a bit fancy will use tree diagrams. But yeah, let's see where we can take this next. Now that we've got some numbers for the probabilities, what would you do next with this, Charlie?
Well, I might be curious. Well, there's two possibilities. The problem that we've got on on your screen,
Hmm.
I think suggests other combinations of numbers and whether we think that any of them would lead to a fair game or.
I mean, I kind of want to see what happens with the interactivity
Indeed,
to
sorry.
see whether it matches up with what we found.
Absolutely, yes.
So shall I reset it so that we can start from no results again?
Okay.
And did you want the graph or the table?
Do the table first and then the graph, please.
Okay, right. And how many times would you like me to run it?
100.
Okay, so I have to click this button 100 times.
No.
Okay, so before I scroll down, what are we expecting? So it was 12 out of 20 and 8 out of 20. So if we've done it 100 times, 8 5s, so it's going to be 60% and 40%. So
40% wins.
40% win, yes, that's what we're expecting. So shall I scroll down?
And what's interesting is, given the previous activity, Alison, look how far away we were from 40% at the beginning. And then slowly, and if we'd done it only 12 times, we might have thought that it was a fair game. But as we did more and more, we sort of start converging. I mean, at one stage, we were exactly at 40%. And there we're at 40% when we get after 70 odd goes. So
yeah, so it seems to go above 40 for a bit and then back down below 40 and then above 40. And if I do another 100 trials, you can see it is still hovering around the 40, but I'm not going as far from the 40, and because we've got the cumulative score, so it's like 0.397. That's pretty close to 40%. So yeah, it's hammering home this idea that if I just do a few trials, then the signal is being obscured by the noise. But if I'm doing it over and over and over and over again, then those repeated trials are getting me to close to the theoretical probability.
So I might, spin a coin 3 times and get all heads, but I'm unlikely to spin a coin 100 times and get heads every time.
Unless it was one of those trick coins.
Okay.
Do you want to tell us a little bit about the graph?
Okay, so this is the graph of what you just saw in the table. So we win is the blue. So you can see the first move was a win, and then the next 2 were also wins. And then so every time we go down and we go left if we lose, and we go right if we win. And so, yeah, so that was a couple of losses and then a couple of wins, a couple of losses, a win, then lots of losses all in a row. Then a couple of wins.
It's telling the story as we go down the page. And so you can pick out the losing streaks and the winning streaks by the big bits of red and the big bits of blue. But you can see it sort of homing in on this sort of 0.4-ish mark as we go down the page.
Yes.
Okay. And you can download the results. So if you get super keen about wanting to do some statistical analysis of these results, then it's possible to download them. Now, you mentioned some other combinations, Charlie. So I think I can get at those either by scrolling down and I can see them, but I can also get the interactivity for each of these variants as well. So this is for set B, which has got 1, 3, 5, 6, and 7.
I wonder, Alison, if we could look again at the 3 sets side by side.
They are.
And without doing any calculating, without doing any writing, would participants like to guess or intelligent guess which of these you would, if you were going to play the game, which of these would give you your best chance of winning? We know that the first set only gave you a 40% chance of winning. Do sets B, C, or D improve your chances? Do any of those give you, say, better than 50% chance of winning? Would you want to play the game with any of those?
How long are we going to give people to think about this?
1 minute max.
Because I can guarantee that some people are already drawing tree diagrams.
I haven't asked myself this question in a long time, so I'm quite curious whether
So I don't have a good intuition for this. And in fact, I don't have a good intuition for a lot of probability stuff. And that's why I do resort to tree diagrams, sample space diagrams, and trying to formally calculate things, because I'm always reminded of that wonderful article that David Spiegelhalter wrote for Enrich once. And the title of it is something like, why do people find probability unintuitive and difficult? And the first sentence is something like, the reason why people find probability unintuitive and difficult is because probability is unintuitive and difficult. Yeah. And I felt really pleased that David Spiegelhalter, who is a leading author on statistics and probability, he finds it difficult. And so it's okay that I find it difficult. And what we can do is we can find strategies for understanding and analyzing it and bringing it more into something that can be calculated with. So I'm thinking that in set B, I've got lots of odds and only one even. So the only way I can get an odd total is if one of the things I pick out is 6. So that feels like I've got good chances of getting even totals there.
But if you compare that with D, where you also only have 1 even, but there are 6 altogether.
So D is, we reckon, going to have a bigger chance of winning than B.
Yes, because they're almost identical.
Yeah.
But the chances of getting even one is less likely. So I think it's a question between C and D. Do you want to have a think about that?
Well, C has got a right old mixture of odds and evens, because it's got 2 odds and 4 evens. I don't know. Andrew's guessed D.
Yes, I think.
And so far, Andrew's had pretty good probability intuition in this session so far. So I'm going to vote with Andrew. I'm going to say that I think it's D.
Okay, shall we try it on the interactivity? I wouldn't bother with B, but let's compare C and D.
Okay. Right, so this is set C, 2, 3, 4, 5, 6, and 8. And okay, that's pretty close to 0.5, isn't it?
Almost a half.
Okay.
Okay, I think D is going to be better than that.
Set D. Let's have a look. Yeah, wow. About 70% it's come out as. And we could sit down and work out the theoretical probabilities now to confirm our intuition and our experimental probability. But I'm quite interested in C because that seems like the closest that we've had so far to a fair game. So is it a fair game? It doesn't look as if it's quite a fair game. Can we work it out?
Well, I think there are 15 different combinations, Alison. And because that's 15 is an odd number, it can't be a fair game.
Yeah, no, you're right.
So I'm going to be, you'd call it cheating, but I'm going to be really lazy about this. And I'm going to say, if the number of combinations is odd, then
It can't be a fair game.
Can't be an equal number of evens and odds.
Okay, so how did you work out that there were 15 combinations?
Because I imagined I can combine the first number that I choose with another 5, and then the next one with another 4, and then the next one with another 3, because I mustn't double count anything. So it was 5 plus 4 plus 3 plus 2 plus 1. So
okay, so it's kind of like when I did Patrick's method of listing them, and I did 2 and 3, 2 and 4, and so on. But I don't know if anybody but me noticed this, but when I wrote them out, it made that nice sort of triangular shape, because I did all of the 2s and all of the 3s and so on along it. And so 15 is a triangular number. And so that all makes sense to me now. Thank you. So can you have a fair game? I mean, not with 6 balls, but.
I think you can with 4 balls.
Okay.
Shall we give everybody a chance to see whether they can find a fair combination with just 4 balls?
That gives you an equal chance of an odd and even total. Okay. Well, I thought I would try 2 of each, 2 odds and 2 evens, and that hasn't worked.
Andrew thinks it does work. It doesn't work for me either.
I think it would work if I was replacing the balls. Yes. But I think because I can't take the same one out twice, I think it doesn't work.
So Patrick, we agree that it doesn't work with 2 odds and 2 evens, but I have claimed that it does. You can find.
Right. Well, I'm going to try
with a total of 4.
I'm going to try 1 odd and 3 evens. So I need someone else to try 3 odds and 1 even, and then we'll have tried everything, I think, because you can't have them all odd or all even, because that's just always going to give you even, right?
Right.
Okay. So I'm going to try 1 odd and 3 evens. Shall I do it on the screen so that everyone can see? That'd be clever, wouldn't it? Right.
You could try 1, 2, 4, 6.
I'm going to try odd, even, even, even. Is that all right?
That is all right.
Because I cannot be bothered to actually think in numbers anymore. Right, so I can't choose the same odd number twice, so I'm going to scribble that out. And I can't choose the same even number twice, so those 3 don't exist. Right, and then I've got an odd plus an even, so they're all going to be odds. I've got an odd plus an even, so they're all going to be odds. And then I've got an even plus an even, so they're all going to be evens. And then all together, I've got 3 plus 3, so I've got 6 odd, and I've got 1, 2, 3, 4, 5, 6 even. So that looks like a fair game. And Laura's tried 3 odd, and it works, and Andrew has agreed. So I think what I'm going to do then is I'm going to start collecting fair games together. So fair games. So 1 odd and 3 evens, or 3 odds and 1 evens. And so the total number of marbles is 4 for both of those.
So can I, shall I offer some help? So I think you can also create a fair game with a total of 9 marbles.
Okay.
So I'd like everyone to, so the challenge for everybody is, can they find a combination of odd and even numbers when you know that the total is 9, that it's going to produce a fair game?
Right, well, I'm going to try 4 and 5 because that's like about equal numbers of each. And so that's like the midpoint. And then maybe we can work out from that, because I know that having all odds or all evens isn't going to work. And we
So
saw.
do you want everybody else to try something else, Alison?
Yeah, I think so. So if I try 4 and 5, if someone else can try 3 and 6, and someone else can try 2 and 7. I don't think 1 and 8 is going to work, because it'll be like that set D that we had before in the 6 balls. That if you've got a lot of, if you've got what.
When you said 4 and 5, you haven't suggested 5 and 4.
Oh, good point. Well, does it matter?
I don't know. Were you assuming that it didn't matter?
I think I might have been. Now, why was I assuming that it didn't matter?
I'm just wondering, on your white sheet, Alison, could you do Laura's combination of 1 even and 3 odds?
Okay.
So
I've got even, odd, 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 even, odd, odd, odd. Because
I think what we might find is that the result, the content of the table.
So even plus odd, 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 even plus odd, 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 odd plus odd. Okay. So yeah, it looks as if I can switch the labels. I apologize for that really untidy drawing. I hope everyone can see it. Okay. But yeah, if I switch the labels around, it doesn't matter, because it only matters whether the two things are the same or different. So if I swap all the evens for odds and all the odds for evens, then it's still going to give the same.
Yeah, because the number of odds and odds is going to be the same as the number of evens and evens. And the number of evens and evens is going to be the same as the number of odds and odds. And in both cases, you get even total.
Okay, so I'm going to do my 5 and 4 then. Odd, 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 even, 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 even.
Okay, before you carry on then, we have Andrew, Laura, Jane, Heidi, and Tara. I'm just wondering whether you want to give each one a job to do, so to speak.
Well, Patrick's doing 6 and 3.
Thank you, Patrick. Yeah, I didn't mention Patrick.
So
maybe 2 people do 6 and 3, 2 people do.
Yeah, and Andrew, do you want to do 6 and 3 as well? And Laura and Jane can do 7 and 2. And then Heidi and Tara, you can do 8 and 1, but I don't think it's going to be fair because of my conjecture earlier. Andrew's already done it. Brilliant. While I've been waffling on, everybody else in the class has been knuckling down and getting on with the work that the teacher set. I'm not going to work all of these out, Charlie. So I've got a 5 by 5 grid here. These are all going to be even, but I'm not going to get these 5 here. So it's going to be 25 minus 5, which is 20. Then I've got a 5 by 4 here. They're all going to be odd. And 5 times 4 is 20. I've got a 4 by 4 there, but not the ones down there. So that's going to be 16 minus 4 is 12. And they're all going to be even. And then I've got a 20. I've got 5 by 4, so there's 20 there. So I'm going to have 20 plus 12 are the even. And I'm going to have 20 plus 20, which is odd. I'm only interested in whether it's the same or not. So I'm not even going to work out what 20 plus 12 is, because I know it's not the same as 20 plus 20. So this is not a fair game. So 5 and 4 doesn't work.
Okay.
So I guess I should record that somewhere. I'm imagining that this whiteboard is now like my blackboard or whiteboard at the front of the classroom, and I'm recording the findings of the class for everybody to see. And if I knew how to do fancy Zoom sharing pen things, I would let people write up their own things on the whiteboard. But I don't know how to do that. So, okay, so unfair games. I've got 4 and 5 and 5 and 4. Okay, 6 and 3 then. Those of you who did it come out as a fair game or an unfair game? That's a very emphatic fair, Patrick, in block capitals. 36 out of 72. That sounds fair to me because I think 36 is about half of 72. So we've got a fair game to add then. So 6 and 3. And we can say that 3 and 6 will also work. Do we need to try 7 and 2 and 8 and 1?
Well, if we in the classroom, oh, you're asking, you mean if this works, then...
If we know that this is a fair combination with 9, can we say that any other combination with 9 altogether won't work? I don't know if we can or not. I don't think I could with a class of year 10s.
Okay. But I am curious about whether you notice anything about the results so far and whether anybody would like to make a conjecture about what other combination of odds and evens might make a fair game. So far, we've had 1 and 3, 3 and 1, with a total of 4, and then 3 and 6 and 6 and 3, total of 9.
I've noticed something about the totals.
So there's something to notice about the total and something to notice about the distribution of odds and evens.
Okay.
Could anyone stick something in the chat that strikes them about the results on Alison's sheet so far?
Ooh, Laura says 1 and 3 has a gap of 2 and 4 is 2 squared. Okay, and that also works for 3 and 6, Laura, because 3 and 6 has a gap of 3 and 9 is 3 squared. So what would it be if we had a total of 16 then? We need numbers with a gap of 4 that add up to 16, is that right? For Laura's rule?
Yes.
Okay. So, well, I can work out what that's going to be because I can do half of 16
Patrick's
and then
worked it out.
go out for, oh, Patrick's way ahead of me. 10 and 6. So our conjecture according to Laura's rule, which I'm going to put question marks around it because we don't know yet if it's true, is would it work if we had 10 and 6 and a total of 16?
Or 6 and 10, of course.
Or 6 and 10, yes.
Can I just respond to Laura's question where she says she's not sure why this works, and just reassure her that we're going to come to that shortly. At this stage, we're really trying to model how we would work with students, and we'd have this information up on the board and we'd want them to make conjectures. And I really like what Alison has just done, which is say, well, this is Laura's rule and we're going to test out Laura's rule. This seems like a really good mathematical way of working, where we've got Laura's conjecture.
And if it works, we'll call it Laura's theorem.
Absolutely.
Because if your man Cauchy and Euclid can have so many theorems named after them, then I think Laura deserves something as well. Okay, so I'm going to do 10 odds and 6 evens. I'm going to do my lazy sample space again. So I'm going to say 10 odd and 6 even. 10 odd and 6 even. Okay, so the odd bits are going to be this diagonal here, and the even bits, no, the even bits are going to be that diagonal there. The odd bits are going to be that diagonal there.
Okay, so where you've got 10 odds and 10 odds, that all those are going to be 100 evens, but you've got to take away the 10 along the diagonal. So that's the same as 10 squared. Would you mind if we wrote it as 10 squared minus 10?
I can write it as 10 squared minus 10 as well. They are.
Because later on when we try to do something algebraically, it might help.
Okay.
And do you want to put a smiley face or something in that? Because that's where the totals are even.
No, I don't.
Okay. 10 times. That's what's going to be 10 times 6.
And then this is going to be 6 squared minus 6, which is 36 minus 6, which is 30.
And we're taking away 6 because we are removing the option where you take away the same number on both occasions.
So I've got 90 plus 30 equals 120. 60 plus 60 equals 120. So it is a fair game. So I can rub out the question marks. And Andrew did it with a tree diagram and also got 120 out of 240. So yes, this is the thing where in the classroom, Andrew, depending on the age of students I was working with and how much tree diagram work they'd already done, I might use the sample space, or I might use the tree diagram, or I might try and persuade people to move from one to the other, because I think it's a good opportunity to practice using tree diagrams, but it's also one of those things where sometimes students might be a little bit more prone to make mistakes if they've not done so much tree diagram work, and so some of them may still need the scaffolding of the sample space. And I think some of the geometric patterns that are starting to emerge come out quite nicely with the sample space. And also notice that I'm not using probabilities here, I'm using frequencies at the moment, which is another nice thing that comes out of the sample space. I don't need to work out that the probabilities are half, I just have to work out that there are equal numbers of odds as even combinations. So yeah, quite a lot to think about there. Okay, so we've got Laura's rule for 10 and 6 is 16. Do we want to try and generalize it then?
Okay.
So we want the total to be a square number.
Yes.
So shall I call it n squared? Yeah?
Yes.
And then I need two numbers here that have a difference of n. So the way I worked out the 10 and 6 before Patrick beat me to it was I thought, well, the halfway point for 16 was 8. And then I had to go 2 up and 2 down from that to get the difference of 4. Does that make sense?
Yes.
So what I'm saying is that n squared over 2 has to be halfway between these two numbers, and they have to have a difference of n. So I have to add n over 2. And I have to have n squared over 2 minus n over 2.
And those two numbers will add to n squared, and the difference between them will be n.
Yes. And so I think with students, I would not rush that nearly as quickly as I've just done. I would probably do another generic example. So we've had n squared where n is 2, 3 and 4. I would pick something like 10 and I would get them to work out what the two numbers would be for 10 squared, and get them to think about how 10 squared is 100. So I want to go to 50 and then go up 5 and down 5 to give 45 and 55. And then I might try it with something else and say, well, what about 15? 15 squared is 225, and then half of that, and then go up by 7.5 and down by 7.5, so that we're moving towards a generalization, but that the algebra isn't providing a barrier for those students who might get a little bit freaked out by it. They're seeing algebra as the tool to record what they already understand, rather than something that gets in the way of their working out. Does that make sense?
I'd quite like to use a little bit of algebra to prove Laura's theorem.
Okay.
Because so far we've got a few results, and what you've done so far is a way of describing Laura's result, but we haven't really proved it. So I would like to, would you mind rubbing out the table on the left, and do me a new table, please? and I'd like to have A and B. And I don't mind whether they're odd or even, because we've decided it doesn't really matter. Okay, and then we're going to have in the top left A squared minus A, and there AB, and another AB, and a B squared minus B. And we know that for the game to be fair, the total of evens, which is A squared minus A plus B squared minus B, has got to be equal to 2AB. Now, I can rearrange this and get A squared minus 2AB plus B squared equals A plus B. And I can factorize the left-hand side to give me A minus B all squared equals A plus B. Now that tells me that A plus B is a square number. So when this game is fair, Laura's right. The number on the right, the total, which is A plus B, has got to be square. And if I now square root both sides, I get that A minus B, so that's the difference between the two, is the square root of the total. So when Laura had a total of 16, the difference was 4, which was the square root. So what I like about this is the algebra is reasonable for many year 10 and 11 students, but it does also prove that the results that we've had so far are correct. I'll be quiet in case you want to add something now to this, Alison.
No, I think that's a wonderful summary. It's such a neat little proof. I think the only thing that we haven't mentioned is what's special about the numbers that we've ended up with for what A and B can be. So the numbers A and B that satisfy this relationship. And that's going back to the observation of, you know, how can we write down what Laura's rule is? And this n squared minus n over 2 and n squared plus n over 2, we might be more familiar with them as being half n, n minus 1, and half n, n plus 1, which some of you may recognize as being 2 consecutive triangular numbers. So again, this problem gives you the opportunity to talk about one of my favorite mathematical facts, which is that if you add together 2 consecutive triangular numbers, you always get a square number. And you can do lovely little geometric arguments for this by drawing out the triangular numbers, or you can just do it using the algebra.
And what's wonderful now is that we can now create an infinite number of games, which will be fair. So, I mean, you had the 10 squared there. So I know that 45 and 55 happen to be, you know, 2 consecutive triangle numbers. Their difference is 10. They add up to 100. So I know I could have a fair game with 45 odds and 55 evens. But, you know, 1,000 times 1,000 is 1,000,000. I could work out 2 numbers that add to 1,000,000 where their difference is 1,000, the square root of 1,000,000, and produce a fair game with.
Yeah, so you're going to have to go to 500,000 and then go up and down by 500, aren't you?
Yes.
So it's quite powerful to be able to say that 400 and I can't do it in my head.
499,500 and 500,500.
If we had that many odd and even numbers in a bag, it would have to be a very large bag, but it would give us a fair game. And actually, that's a really nice way to round off. I mean, you might not do all of this in one lesson. It might be in a series of lessons instead. But a really nice way to round off working on a task like this is to be able to say who can work out with this really, really big number, because then you're sort of showing the power of generalization and the fact that you can use algebra to encode that generalization so that you don't have to write down every single example. And even cynical year 10s and 11s still get a little bit of a buzz from saying, I can do this with 1 million. That's quite cool. So,
especially, I mean, we rushed the beginning a little bit. I gave you the hint that a total of 4 would work and a total of 9. With some classes we've worked with, we've let that, we've let them struggle for a lot longer, which means that when they actually do find Laura's theory, then Laura's theorem, then there's just that added excitement that they've got something that's going to save. It was very difficult to find combinations that worked initially, and at the end we can just do them at the drop of a hat. That feels very powerful. I did show this to a group of teachers once, and next time I saw one of the teachers, he said that the following day he'd worked on this problem with every single class that he had. So he had some year 7s and he did just some simple sample space diagrams. And then others in year, 8 or 9, had started doing some work on tree diagrams, but he'd also done the proof with some 6th formers. So the whole day was spent working on odds and evens. So yeah, it's a nice problem to revisit. We've got a little bit of time left to show 1 or 2 other.
Yeah, I want to show a video clip next, because I think it sort of introduces the other thing that we wanted to talk into quite nicely. So some of you may have seen this before. I'll put the link to it in the chat in a moment as well. But we're just going to watch. So the setup, I'm not showing you it from the very start. This is Matt Parker showing how to flip a coin 10 times so that it alternates between heads and tails each time. So let's have a look at that.
Okay, let's start this thing. First one out. Heads, followed of course by a tails. Now, I actually find the first 5 of these are really easy. You pretty much just chuck it in the bowl 5 times and you've got your first heads, tails, heads, tails, heads. After that it gets a bit trickier. I really struggle with 6 and 7. I mean 8, piece of cake. 6 and 7, much harder. So here we go. Let's go for a tails. Come on. Yes, 6 and then 7. Nearly out of the woods. There's 7. Ah, nice job. 8, like I said, piece of cake. Chuck it in there. There's 8. And then finally 9 and 10. This takes a little bit of focus because there's only a 1 in 1,000-ish chance that this will work. So here we go. Ready, and 9. Yes, and then finally for 10, alternating heads, tails in a row. 1 last flip. There we go, and there it is. That is 10 coin flips in a row, perfectly getting heads, tails all the way down. And
okay, so I don't know if anyone in the chat has seen this before. Matt's not the only person to have done a video on it, but I do quite like his take on it, because he does the alternating rather than getting all 10 of them being heads, which other YouTubers have done. And I think Darren Brown famously did it as well on one of his shows. But I do think that clips like this, and I'm just popping the link in the chat for you all now so that you've got it. It's fairly easy to find if you just look on Matt's YouTube channel. Clips like this can be a really good way to sort of provoke some discussion about probability, because the immediate question is, how on earth did he do it? And of course, the way he did it was by being a heck of a lot more patient than most of us are, and sitting and filming and managing to keep up that level of enthusiasm and that pattern, that commentary, despite the fact that by the time you see that, he had been filming for a really, really, really long time, because getting alternating 10 heads and tails like that is, well, it's a 1 in 2 to the 10 chance, which is about a little bit more than 1 in 1,000. So it's a really nice prompt to just show that section of it and to say, how do you think he did it? Is he really, you know, some sort of gifted magician? Was there any special tricks? So Tara, that's exactly what he did. He had to keep filming over and over again until he got the alternating sequence. And so quite often it would be like he'd go heads, tails, heads, heads, and so it would fail on number 4, or heads, tails, heads, tails, heads, heads, and fail on number 6. So he kept on failing in different places, but then eventually, because he kept filming and, you know, devoted far too long of his life to it, he managed to do the 10 flips in a row. So there's a couple of Enrich activities that are getting out the same sort of thinking. And so the first one that I want to show you, it's called Last One Standing. And this is one that if you ever have the opportunity to do, can everyone see that okay? If you ever have the opportunity to do maths with a large number of people, like an assembly hall full of people, you can do it as an activity. But if you don't have lots and lots of people to do it, you can use the Enrich interactivity to do it instead. So if we had a class of 30 people, well, we can do different things in the settings here. You'll notice these are all powers of 10. So we might start with 16. We might try 64 in a minute. And what you do is you get everyone to stand up, and you can either flip a coin, or you can get everyone to flip a coin, or you can just flip one coin and get everyone to choose heads or tails before. And I've seen this done quite nicely, where if you're choosing heads, you put your hand on your head, and if you're choosing tails, you put your hand where your tail would be, and that way you don't get the problem where people change their mind. But what the Enrich activity does is it flips the coins for you, and it just shows you what the distribution looks like after each number of flips. So in this case, it took 4 flips to get everybody flipping tails and sitting down. So this last person standing had got 3 heads in a row, but then on their last flip, they got a tail. And if I change it so that instead of having 16 people, I have 1,024 people, that would look like this. So in the chat, please, how many goes do you predict it's going to take for me to get everybody sitting down? So Patrick thinks 11, Tara thinks 8. If you've got a justification for your guess as well, that would be nice. Well, think about how many people you'd expect to be standing up after each step. So when I flip the coins for the first time, what do we expect is going to happen? Half is going to sit down each time. So how many people roughly will there be after one flip?
Yeah, when I was trying to guess this, Alison, I was halving and halving and halving. So 512 and 256 and if you keep going.
Well, let's see what happens then. So if I flip the coins, so yeah, about half of them have had to sit down. So we've got 535, so a little bit more than 512, but fairly close. And then again, yeah, 260, so about half of them have sat down again. And you can see the screen is gradually changing. All of those tails don't get to flip again because they're sitting down. And this is why when you're doing it like in the school hall with a large number of people, you will get some people sneakily trying to change what they did, which is why the interactive is better, because computers never cheat. So we've got 139 after 3, 71 after 4, 31 after 5, 18 after 6, 7 after 7, 4 after 8, 1 person remaining after 9, and then no people after 10. So yes, 10, 11, those guesses were about right for this. So I'm just going to stop sharing a second. So yeah, what this shows is that for that one person, they're going to feel really special. That person who got 9 heads in a row, they're going to feel as if there's something special about them, but there's nothing special about them. They were 1 in 1,024 people, and they were the lucky one. And so this is addressing another probability misconception, which is this idea that you get these headlines about super rare sensational events like 3 generations of a family all having the same birthday or something. And when you start digging into the probability of it, you find that this particular family is one of however many millions of families in the UK, and the probability is, if it's a 1 in a million chance, you'd expect there to be half a dozen families that shared that. And it feels very special when it happens to you, but we should expect unlikely things to happen to somebody. And that's one of these places where the maths is meeting the psychology and the when you're thinking about risk taking and when you're using statistics to help you to understand risk, then understanding that just because something happens to somebody doesn't mean it'll happen to everybody, and that you can predict what will happen to the population, but predicting what will happen to individuals is very, very difficult.
Yes, we knew that it was likely somebody might get 9 or 10 heads in a row. We just didn't know who it was going to be.
Yeah.
That again, also, there's nothing special about their diet or their exercise, or in the same way that these families who maybe have 10 boys or 10 girl children, if there are enough families having that number of children, somebody will have 10 boys or 10 girls.
And then I think it is worth showing, I know we've not got much time left, but it is worth showing the other lovely simulation activity that we've got on Enrich, which is called Same Number.
Sorry, can I just stop you a second, Alison? Because Patrick has mentioned in the chat Darren Brown's experiment with the horse racing, which was very similar. And I think what he did is he had groups of people, and the people who won the first time then were split up into 6 different groups, and they were all given a different horse to bet on. And then 1/6 of them had the right horse. So they then slowly built up more and more. And so there was a group of people who won the first time and then won again the second time and won again. And eventually there was somebody who'd won, I don't know, 6 or 7 times in a row. And so they were convinced that Darren Brown had sort of magical powers and were prepared to mortgage their house on the next race. And Darren Brown was making exactly this point. And Patrick's put a link in the chat to the program.
Yeah.
Same idea.
Okay, so the last interactivity that I want to show you is the Enrich take on the birthday paradox, which probably a lot of you will have heard of before. So the birthday paradox says that if you want a room in which there's at least a 50% chance that 2 people share a birthday, how many people do you need in the room? And people are very surprised that it is only 23. Once you've got more than 23 people, there's a more than half chance that people share the birthday. But the same number experiment sort of takes this, but goes even further. And it's quite nice with a class of 30. And if we'd had more people here today, then we would have had a go at it in the chat, but there's not many of us, so we'll just use the simulator instead. So if we have 30 people, if we have 30 people and we ask everybody to choose a number between 1 and 225, you might think that because they've got 225 numbers to try and hit, there's a really low chance that 2 will hit the same number. So we get the computer to simulate it. There are their guesses, and then we get the computer to look to see if there are any duplicates. And actually there were loads of duplicates. So 2 people picked 15, 3 people picked 181, 2 people picked 170, and 2 people picked 43. And you can do this in your classrooms. You could say, if you've got a group of 30 kids in the class, you can say everybody write down a number between 1 and 225. And if you work through the maths of it, it turns out that something like about 5/6 of the time, there will be duplicates. So we can do this over and over again. And I've not yet had a time. There we are, no duplicates that time. So a couple of times there were no duplicates, but overwhelmingly there were duplicates. And so we suggested on Enrich that this is a stage 4 challenge level 2-star activity, because I think it is worth doing the maths behind it to work out how it works. And if I just show you on the site, as with most Enrich problems, you've got the teacher's notes. So there's the problem. You've got the teacher's resources there, and the teacher's resources takes you through how you can work out the probabilities, and how you can get these key questions to tease out why it is much more likely than you think. And this is also a very nice opportunity to introduce the key idea that when you're working out probabilities, sometimes working out the probability that something will happen, it's easier to work out take away the probability that that thing doesn't happen.
Can I just check, Alison?
Mm-hmm.
Did you mention where the 225 came from? That it was...
Oh, I didn't know.
The square of half of 30. So when there were 30 people in the class, half of 30 is 15. 15
squared is 225. So if you had the opportunity to do this with an audience of 100 people, you could do half of 100 is 50. 50 squared is 2,500. And so you get your 100 people all to write down a number from 1 to 2,500. Nobody thinks there's going to be a duplicate, because like 2,500 is a really big number. And yet it's overwhelming odds that there will be a duplicate somewhere in the audience.
And it's great because you get people from the audience to start reading in order, I don't know, from the front of the room or the back, just to shout out their number. And if anybody else has got their number too, and very early on, people get really excited when their number's been shouted out.
Yes, yes. I think we're out of time, Charlie. What else do you want to say before we finish?
The half n all squared little formula is in the teacher's notes that you just showed.
Yeah. I mean, I hope we've given everybody some food for thought when it comes to teaching probability and some of the key ideas that come out. And it would be lovely if some of you will take these away to the classroom and have a go at them. And obviously you can get in touch with Charlie via the Enrich website, or you can find me on Twitter or on my website, which is alisonkiddle.co.uk. And yeah, it'd be lovely to hear from anyone about how to get on. I'm going to hand back to Patrick to do some last minute housekeeping, but thank you very much for your attention and for joining in, everyone. Really enjoyed it.
Thank you very much, Alison, and thank you very much, Charlie.